welcome to another lecture of whatever class this is. So let's get started for the day. Some announcements and things, and then we will do technical stuff. So, in terms of announcements, I believe you have a homework due today. Is that right? So be sure to, get started with that. But beyond that, so your next homework can also go out today. I was just looking at it this morning because I'm disorganized. And I believe this homework is actually substantially easier than the current one. Yeah, Leticia agrees, so that's good. As usual, you can go ahead and get started with it. It'll incorporate a few elements from the current go-round of the course moving forward, but relatively small, and it's good for you guys to be peeking ahead anyway. So this next homework will be a little bit more machine learning oriented in a sense. Like we'll implement a small classifier and prove some cool stuff about the kind of numerical routines along the way. In particular, in this class, we focused a lot on overdetermined problems in linear algebra, meaning like least squares and things where like you solve ax equals b and a has a bunch of rows. In this homework, we'll examine the underdetermined case, like what happens if you want to find solutions to ax equals b and a has more columns than rows. So for example, for our friends in biology, this happens all the time. You measure gene expression or whatever, and you get like 1 million features that come out of your data, which is way bigger than the data set you can collect. And now you need to put some prior on the features that you care about. In this particular assignment, what we'll look into is the prior where you want your coefficients to be relatively small. And then you'll show the kind of the naive implementation you'd probably do in PyTorch anyway, like just gradient descent starting from 0, actually is guaranteed to reach the minimum norm solution of the least squares problem, which is kind of cool. So like essentially if you code the wrong solution by accident, you probably ended up in an okay spot. And beyond that, a reminder that your midterm is coming up. I think it's the 22nd. I actually looked at the calendar this time. So I think in the coming week, maybe Leticia, Mark, and I will schedule some review sessions, find a room, all that good stuff. And I will, if somebody reminds me, I'll release like an old midterm or two for you to practice. I can't help but provide life advice. So midterms are written things, and they're in a room. You're by yourself. It's a bit of a different experience than doing your homework. Sadly, I won't be here to do it for you. My strong suggestion, this is just as life advice because I feel like students often make the same mistake. Take the practice midterm under conditions that simulate your actual midterm. So like put on a timer, go in a private room, whatever, and take it. And at least for me, I can tell you what helped me a lot in college and grad school, which is you take the practice midterm. Sadly, by the way, we'll release the midterms, but not the solutions. So you'll have to come by office hours to get help with those. You're giggling as if it's a top secret thing, but the reality is I just never wrote them because I don't know, we don't need detailed solutions. However, here's the thing: unless you got 100% on that practice midterm, my suggestion would be just take the same one a second time. Our students always hear this advice and they don't do it, but trust me when I say you'll be surprised by how poorly it will go the second time. Because I think there's a very big difference between reading the solution to a math problem and actually articulating it and writing it down on paper. And that is the #1 mistake that I see in courses like this. Like people will happily read through solutions to homeworks and exams and whatever, and like kind of agree with it, but that's very different from having to actually commit it to paper without being able to look at stuff. Does that make sense? Okay, cool. So with that, we're going to continue from our previous lecture. So I'm not going to lie, like some lectures go really well, and then some of them like maybe not so much. The previous lecture was like maybe not the finest lecture I've given in my career. So we're going to do a little bit of cleanup at the beginning of today's lecture for some things that I rushed and babbled my way through. And then we will talk about all of the delightful and exciting applications of the singular value decomposition, which is like the big daddy of matrix decompositions. Okay, any questions, comments, concerns so far, by the way, before we get started? Cool. I really hate this microphone. It's like very loud. Okay. Right, so in a fit of mathematical craziness at the end of last lecture, I thought I could derive the SVD, which is the last matrix factorization we're going to need in this course. And of course, I rushed through it and I think confused 85% of the people in this room. So I figured a good thing to do would be to start today's lecture by deriving it in a slightly more peaceful fashion. And then we'll go through some applications of this thing. But then I did a bad thing, I'm sorry. Which is this morning, I thought, well, that would be boring to just repeat lectures, so I should come up with a different proof of SVD, which of course is not in the textbook, so I worked it out on my scrap paper, and what that probably means we'll do it together and we'll get confused midway through, and then you're even more confused about SVD than you were at the last lecture. Okay, so that's our plan to start for today, and then after that, we'll go through applications. That part I'm confident in because it basically describes my everyday life. Turns out I've built a whole faculty career basically on just like plugging SVD into problems and doing a little bit of like math around the outside. Okay, so why do we like the SVD? Like in some sense, here's what's going on. So we spent several lectures talking about eigenvalue problems. And it sort of follows exactly the same structure that we've talked about a lot in this course. Remember, we talked about like LU, and then we spent a bunch of time motivating Cholesky factorization because we noticed that a lot of our matrices were structured in a particular fashion, right? And in that case, like symmetric and positive definite. Now, for eigenvalue problems, we kind of did the opposite of that in the following sense. In a sense, this is sort of classical linear algebra's fault for determining the order of topics in this course. But in some sense, we started with eigenvalue problems, and we certainly did a bunch of examples, and I would argue two things were true among the examples we had. One is that they were almost all symmetric and positive definite, which kind of hints to us like maybe there's a little more to life than the basic eigenvalue problem. And moreover, like we had to do a bunch of work to justify that the problem even has a solution, right? So for example, for asymmetric matrices, we show that there's one eigenvalue, but it might be complex, and like it's not clear that there's more eigenvalues, and so on, right? So what would be really nice in life would be if there's some eigenvalue-like decomposition of a matrix that doesn't require all of this like, you know, glitter and confetti around the outside in order to make it work, right? Like if we just have one, you have any matrix and it admits something that has some nice properties in common with eigenvalues, but doesn't require so much justification. And that, from my perspective, is sort of a reasonable way to think about the SVD of a matrix. That like, for 82% of the applications of eigenvalue problems, probably the SVD is sufficient, and moreover, it exists for every matrix, right? So we don't need to like go through a bunch of existence, uniqueness, whatever proofs. Does that make sense? Okay. So as promised, I scribbled out my own proof of SVD this morning. You know, it's a good just like life exercise. Like every morning you brush your teeth, or like I switched to that like. My dentist suggested this like vibrating whatever toothbrush recently, and like I feel like I jarred every time I wake up in the morning. But in any event, whatever you do in your morning routine, you should do that and then sit down and write a new proof and derivation of the SVD because there are many. So the course notes contain two. One is the one that I like mumbled my way through in the previous lecture, and then there's a second one which kind of does the following. Basically, I think all of the SVD proofs kind of make the same, use the same fact, which is as follows. Basically, we like eigenvalue problems, but we don't like the fact that not all matrices have eigenvalues. And so a reasonable thing to do is to try somewhere in your SVD proof to like construct a symmetric matrix, right? Because we know the second that we're symmetric, then we have a full set of eigenvectors and eigenvalues. So the previous way that we did that was by looking at critical points of this Rayleigh functional, which basically amounts to looking at A transpose A. There's a different proof in the textbook that kind of constructs a matrix that looks like 0, A transpose 0. This thing is square and symmetric even if A is not. And then you can pull the SVD out of that. That proof is very efficient, but I don't think it's very geometric in nature. Like it's not obvious what the SVD is telling us about life. But this morning, because I don't know, I get bored teaching the same thing every year, I thought we'd try a slightly different proof. Which is basically just a matrix version of the one we did last time. So to get started, let's suppose that we have A is an M by N matrix. Now, unlike the previous couple lectures on eigenvectors, we make no assumption on A. It could be all zeros, it could be square, it could be non-square, it could be wide, it could be tall, whatever, right? And our goal is to derive some eigenvalue-like decomposition of A without all the assumptions we need to make eigenvalues work. So remember I told you that at some point in life we're going to need a symmetric matrix, and so maybe we take a clue from our last lecture and we look, by the way, I'm going to choose to do this with AA transpose. You could have done this with A transpose A, it's exactly the same proof. Okay, so let's take a look at the matrix AA transpose. Now for one thing, this is, let's see, an M by M matrix. and it's symmetric. Now, if we recall, there's a really famous important theorem from linear algebra called the spectral theorem, right? And that tells us anytime we have a symmetric matrix, it actually doesn't have to be invertible or positive definite. We have a full set of eigenvalues, and their corresponding eigenvectors are orthonormal to one another, right? We sort of justified that a few lectures ago. But in particular, if we want to be efficient about it, what that means is we can write A transpose is equal to U sigma squared U transpose. Now, I have chosen to do a sneaky thing. Remember, actually, a couple lectures ago, we actually showed a second thing about this matrix, which is that all of its eigenvalues, they don't only exist, but they're also non-negative, right? So in particular, rather than writing the usual thing, which is a diagonal matrix of eigenvalues, it's perfectly fine for me to write that thing squared. Now you can probably see where I'm going with this. Is this okay with everybody? Okay. Moreover, we have U transpose U is equal to the identity because this is a set of orthonormal eigenvectors. Yeah?
Just remind me the property that lets you write U transpose or like decompose A transpose like that?
One more time?
Can you just remind me like the property or like the argument for why A transpose equals on the right hand?
So A transpose is a symmetric matrix. And so this is just a byproduct of the spectral theorem. So the columns of U are the eigenvectors and the sigma squares are the eigenvalues.
Thank you.
Yep. Okay. So now what we're going to do, which is kind of fun, remember from our previous lecture, what we tried to do was like critical points of A transpose and A transpose A have to do with like looking at lengths of vectors as they get mapped by A or A transpose from one space into another. So here's a kind of reasonable fun thing to do. Let's take this relationship and pre-multiply it by A transpose. Okay, because then we'll have A transpose A times something. Yeah? So in particular, let's look at A transpose A now times A transpose, which basically is the same as just pre-multiplying this expression by A transpose. So like in particular, this is A transpose, A transpose. So now let's substitute in, and we get A transpose U sigma squared U transpose like that. Cool? All right. So in particular, because U is orthogonal, I can post-multiply this expression by U, right? And what I'm going to get is A transpose A transpose U is equal to A transpose U sigma squared. Cool? Y'all awake yet? I know it's super early for grad student time. You had to wake up for this class. I appreciate that you're here. Okay, so it's important not to think too hard about expressions like this. Like this feels complicated, but like at the end of the day, this object is just some matrix. Okay? Let's say that one of its columns is non-zero. Right? So I take one of the columns of A transpose U, it's non-zero, I pre-multiply it by A transpose A. What's on the right-hand side? Well, you take that column and you scale it by an element of sigma squared. What can we conclude about the columns of A transpose U? At least when they're non-zero. Yeah?
They're eigenvectors of A.
That's exactly right. So the columns of A transpose U, what we just showed, is that they are all eigenvectors of A transpose A, or they're equal to 0. Does that make sense? So basically, what did we show? We showed every column. Oh, no, I keep bumping into this thing. Okay. So every column of A transpose U is either non-zero. Oops, the S stands for 0. Or an eigenvector of A transpose A. And what's going to be the eigenvalue? Like sigma I squared, right? Because it's in this expression. Okay, so notice that this is just like a slick version of an argument we did in the previous lecture. We have eigenvectors of A transpose, eigenvectors of A transpose A, and now they're kind of related to one another. We have not shown that they're unit norm, by the way, but we have shown they're both eigenvectors. Yes, we hear. That's right, because 0 vectors are oh, sorry. are 0. Thank you. Anybody else, or it was just like 8 of you jumping on the same mistake? Okay, fabulous. Okay. By the way, just for fun, so let's say that I take one of the columns of ui, and I did get 0, right? Let's like dig into that case a little bit. So in particular, let's say A transpose ui is equal to 0. Basically, I'm going to keep doing the same trick, right? I can pre-multiply this expression by A, right? A transpose ui is equal to 0. But remember, like, what is U? Well, it's the eigenvectors of AA transpose. So in particular, we showed that sigma I is supposed to be 0. That makes sense? So basically, this just gives an alternative way to understand the previous statement. Like, either the eigenvalue of AA transpose is 0, or I mapped to an eigenvector of A transpose A. Cool? Notice this, again, just to keep repeating myself, this is just a slick version of the proof we wrote last time. We're kind of doing it for all columns of A in one shot. Okay. So we're actually most of the way to computing the SVD if we do it in this like kind of slick proof, which is good because I packed too much in today's lecture. Okay. SVD is fun. Like, this is a cool one because like it unlocks all of linear algebra. Okay. So here's the trick. This is the innovation in my Scratch paper from a few hours ago. So we're gonna do it together. We'll see if it works. Okay. So let's say that we're gonna take U, and we're gonna divide up its columns. So the columns of U either have 0 eigenvalue or non-zero eigenvalue. Yeah. So in particular, we can write U is equal to U bar U naught, where here the sigma i's are not equal to 0, and here the sigma i's are equal to 0. Okay. This might require reshuffling our eigenvalues, but that's not a big deal. Cool? Okay. Now, here's a fun thing we can do. We're going to define a second matrix, V, to be V bar V0. Okay? And you can probably guess where I'm going with this. Essentially, the V bar is going to be the image of the U bar, which remember is non-zero under A transpose, but I'm going to divide them by their norm. Okay? So in particular, let me write that out, where columns of V bar are normalized columns of A transpose U bar, right? So basically what we showed previously is that if I take anything in U bar, which has sigma I not equal to 0, and I multiply it by A transpose, I get something non-zero in its image, so I can just divide it by its norm, and by definition, I'll call that V bar. Okay, so V bar has a bunch of eigenvectors. I've lost you guys so far. Yeah. What is V0? Good question. I forgot to finish my sentence. And V0 contains an orthonormal basis for the null space of A transpose. Now, let's think about what I just did. By the way, there's going to be a case where like V0 is just empty, and that's actually fine here. But like essentially, well, what did we show? Like, notice that V bar contains a basis for the image of A transpose, right? Kind of by definition. And so what we're going to do is just take all the rest of that space and stick it in something called U naught, or V naught rather. Okay. Yes, great observation. So in particular, V is an orthonormal basis for Rn, the column space of A. Absolutely, good call. And we're going to use that in like t minus 8 seconds. Okay. So now we're almost done with our proof of SVD because already I'm behind in lecture, which is good. So here's the thing. U is an orthogonal square matrix by definition, right? That's the thing that came out of the spectral theorem. right? I've divided U this way, but it's just an orthogonal square matrix. V, as our colleague just suggested, is itself an orthogonal square matrix in this other space. So now all we got to do is make sure that we sneakily basically chose the proper decomposition that's on the screen here. Now there's a little bit of an annoyance, which is that sigma had better be non-square in order to make this product parse, so we're going to have to change our notation a little bit. And I'm noticing that's where my scribbles were a little sloppy, but we'll try to fix it now. So in particular, let's look at the following product. U transpose AV. You guys see what I'm doing? This is like kind of sneaky. Like essentially, I have to be careful like what's the definition and what I've constructed so far. I have defined U and V, so it's perfectly kosher for me to just look at what U transpose AV is. And so long as I get something kind of diagonal looking, I'm done, right? So that's what's left to verify. So what is U transpose? So here's the thing that I can do. I can parenthesize it like that, right? So that is the same thing as A transpose U transpose. Cool? All right. So what's A transpose U? Well, it's really A transpose U bar, and then A transpose U naught, all of that transpose V. Cool? All right. So what is A transpose U naught by definition? One more time, a little louder. Third time, even louder. 0, that's right. Because in fact, I even was strategic and put a 0 there so you would remember that I chose U naught to be a basis for the null space of A transpose. So by definition, this product is 0. Cool? You can see we're so close, we can taste it. Yeah? Okay. Moreover, what is A transpose U bar? Well, remember that I chose the columns of U bar in a really sneaky fashion, right? So if we go all the way back here, the transpose of, the A transpose U generically, which is like the full matrix, and then A transpose U bar is kind of like truncating a few columns of it. What is it? Well, basically, I just get a scaling of that matrix by the sigma i's. Now, I have to be careful. I've extracted the non-zero sigma i's here, right? So in particular, I claim that this thing is really equal to U bar. I'm going to give this like funny notation, like sigma non-zero. Right? So this is like a little square diagonal matrix of the non-zero elements of sigma. And then a 0, transpose V. Sneaky, huh? Isn't that cool? Oh, oops, wait, that should be, I'm sorry, I got that a little wrong. Only a little wrong. We defined V to be the columns of this thing, right? Without the bar. Oh no, now, see, I make one mistake and then I lose you guys. All right, stay with me. It's a very small mistake. Remember, I defined the columns of V bar to be normalized columns of A transpose U, right? So in particular, I have an A transpose U there. So the small mistake I made is that should be a V. That's all. Yeah. Everybody with me? Did I lose you? I know it's the morning. And this is what happens. I make one mistake, and then immediately your eyes all go down to your laptops. It kills me. Okay. Now we believe it. Yeah? Now remember, like, what is V? Well, V is really, I've got two pieces of V. Like that. Okay. Yeah. Okay. So here's what's going to happen. So I do the transpose. So I will get, this guy is non-square. I've got a V bar transpose like that. 0. V bar V0 like that. Everybody with me so far? Do you see that a magical thing's about to happen? Unless I made a mistake, which unfortunately, because I see your hand, is likely to... Oh, so I just took the transpose of this matrix. So it is sigma times V transpose.
V bar transpose.
That's right. Good. I'm nervous because I wrote this with my like scribbles and now I'm kind of doing it off the top of my head, but I think we're good. So in particular, what is V bar transpose times V bar? Well, if I think about it, I just chose V bar to be an orthonormal basis. So that just goes away. So I get sigma non-zero, like that's this guy, These guys are orthogonal to one another by definition. And then here we have 0. Cool? Notice that I just derived the SVD. Because essentially, now if I pre-multiply by u and post-multiply by v transpose, which is okay because they're square and orthonormal, right? Then I get u times a diagonal matrix, because there's a diagonal non-zero in the upper block and then a bunch of zeros, v transpose. Cool? So in other words, I have shown that A is equal to u sigma. I should be careful, like a little squiggle maybe, v transpose, because I had to kind of pad with zeros, but that's okay. But like zero padding doesn't affect the diagonalness of a matrix, as long as the diagonal part's in the upper left. Cool. All right, so my apologies for rushing through the proof of SVD, but the good news is now you have the one in the textbook and one that I just made up this morning, and I think they all work out. Or at least one of the two is correct, which is good enough. Cool. Okay, so here's the thing. Did this proof require making any assumptions on A? No, none, 0, zip. And so unlike the eigenvalue decomposition, this beast on the board exists for any matrix A, and that's super useful. Now here's a good life philosophy. Anytime you are encountered with a problem that involves a matrix and you don't know what to do with that problem, you should plug in the SVD and see what happens. And chances are with like 85% likelihood, it will solve your problem. Okay? You already saw one example of that, I hope, on your homework, or you will this afternoon. So now we're going to see for the rest of today's lecture a bunch more examples where exactly that kind of thing happens. Okay, so that's our plan for the rest of today, is to just go through all kinds of different places where the SVD is useful. I'm guessing, because I'm talking too much this year, that we're going to bleed into the next lecture, and that's okay. Okay? All right. So here's a fun one. Yeah, so here's, by the way, here's our SVD. We should talk a little bit at a high level before getting too far. Like, what does the SVD tell us about life, and why is it so cool? Notice it actually, is a very fundamental fact about linear algebra. So, A is a generic matrix. It's any transformation from one space into another that's linear. And basically, we proved a really crowning theorem. I mean, we did it in kind of an unceremonious fashion, but notice it says something really deep, which is that any linear transformation can be decomposed as basically 3 steps. Like something orthogonal, so something that rotates, scales, or flips. Not scales, sorry. Something that rotates or flips. And then something that just scales the axes, and then something that rotates again. And that's it. It's the only thing that can happen. There's no other linear transformation out there in the world. Right? That's an interesting fact, and I would argue is extremely non-obvious from just the definition of linearity. And so it's definitely a crowning achievement of numerical linear algebra that such a thing exists. Incidentally, the history of the SVD is kind of interesting. You might spend a little time digging into it. Eigenvalue problems go back forever. The SVD is kind of a modern construction. It comes from demands in numerical linear algebra world, although I think there are some early rumblings that it should exist. But really, it was the numerical community that made this thing super popular. It's kind of interesting that way. So for example, if you took linear algebra in the 1980s, it was a dark time, you probably would not have defined the SVD. This is sometimes I think even in MIT's undergrad class here, I think we do, but that's a pretty modern development. I should note there are so many ways to derive the SVD. A second one is to look at eigenvectors of this matrix B, like I mentioned at the beginning of the lecture. You can take a look in the textbook for the proof for this guy. I should also note that just like when we talked about QR, there are many different things that people call the SVD. The terminology gets messed up in software products all the time. So in this class, I try to be careful about the following names, but to be clear, I will never on an exam ask you the difference between thin and compact SVD, because that's a goofy question. But essentially, like you saw, there's a bunch of zero padding that happened when we constructed this thing. And so there's different versions of SVD that require either U and V to be square, and then sigma is the non-square guy. That's what we constructed on a board. But there's other versions. So for example, you could imagine removing enough columns so that sigma is square. So you kind of look at the minimum of M and N. Or if you are really good at computing eigenvectors, there's a case which we typically is called compact SVD, where you actually slice out. It's not just a minimum of M and N. You can imagine having a null space in both of those, and then slicing out even more vectors. It doesn't really matter. Essentially, it's pretty uncommon to worry about this beyond reading the documentation of the software you're using before you call it. Yes?
Yeah, it's just the final step here
That's right. So like in the proof that we did today, notice that we defined u and v to be square. That was sort of critical for the construction that I made. If you wanted to then construct these other SVDs, essentially you would just do out the product u sigma v transpose, and then just notice that you end up zeroing out a bunch of columns and rows of u and v. Yeah, good question. Okay, so there's all kinds of strategies out there. Those are two. There's even more specialized ones out there. Notice that from an algorithmic perspective, we're now good. Like the kind of funny thing about SVD is actually in this class we will not cover any algorithms for computing SVD because we kind of already did, right? Both of these things basically reduce the problem to an eigenvalue problem. The second one is slightly more better conditioned, for basically the same reason that like the first problem, remember, it squares the condition number of a matrix. The condition number of eigenvalue problem is not quite the same, but it also kind of squares the range of eigenvalues in your matrix, which is the condition number. So the second one is usually advisable numerically. And just like we talked about in the last lecture on eigenvalues, very typically, as we'll see momentarily, what you do is you compute a truncated SVD. Like you don't even compute the full u and v, just the ones corresponding to a few big or small sigmas. Cool. So if you take a more advanced course, you will spend lots of time talking about numerical algebra routines that are specifically for SVD. But actually, they're relatively rare. Like I think you can understand a lot of them just by kind of taking one of these two matrices and plugging them into an eigenvalue method. Like that's basically what's out there. Okay, so what we're going to do for the rest of today's lecture is talk about all kinds of different things we could do with the SVD. And there are so many. You could do this for days. It's like a fun trivia game. The very first one that we can do is just solve linear systems of equations. So let's say that A is square and invertible. I'm erasing this. I hope that's cool. If not, well, it's too late. So suppose A is square and invertible, and I want to solve our favorite problem, AX equals B. Notice that in particular, I can write u sigma v transpose x equals b, right? Now, in this particular case, what do I know? So u and v are now the same size because A is square. And if A is invertible, what do I know about sigma? Can it have any zeros down the diagonal? No, right? Because if it did, then A would not be invertible. It's easy to double check that. So in particular, I can invert this thing one matrix at a time. So what am I going to get? I will get V sigma inverse U transpose. That one is supposed to be U, sorry, times B. My apologies, that was bad handwriting. Let's try that again. That's a U. Okay. Now, notice, like, I haven't written anything particularly profound, but this is a really, really easy expression for solving a linear system. Do you see that? Because here we just inverted orthogonal matrix. What is the inverse of sigma? Well, it's just a diagonal matrix of 1 over the eigenvalue, or singular value, rather. So essentially, my point is SVD is a really powerful object, which should suggest to you guys that it's expensive to compute, right? Like essentially, this thing subsumes everything we've done in the first couple lectures. So that's one expression, but actually a kind of cool thing that I think we can do, that I think is worth doing because actually I see it abused a lot in the machine learning literature, so now I get to get on my soapbox and teach you guys why it's a numerical mistake. Is to think about not just the inverse of a matrix, but something called the pseudo-inverse of a matrix, which I think a lot of people use out of convenience and don't realize that A, it's numerically unstable, and B, it's hard to compute. So let's talk about that object for a minute. So in particular, suppose I wanted to solve AX equals B, but like I'm not so lucky, like A is non-square, it might be tall, it might be wide, whatever. So now the best that I can do is AX is approximately equal to B, like that, right? And so far in this class, you guys are now programmed to do one particular thing, which is to say, aha, well, if I can't solve this thing exactly, I should solve some least squares version of it, like min over x of A, x minus B, and the 2 norm. Yeah? Hopefully you're sick and tired of this formula by now. Cool. All right, so what does this imply about x? Oh my god. Yes, Alice. It solves the normal equations. In particular, we have A transpose A x equals A transpose B. Now here's like a weird thing to think about. Suppose A is not invertible and is like maybe even wide, or like A is the zero matrix. It's like an extreme case. Like, by the way, as you guys solve homework problems or just like problems in everyday life, like you should always plug in like the zero matrix, a diagonal matrix, the identity matrix, and like a few other dumb ones. Notice this problem is actually perfectly well defined for the zero matrix, right? Like, in fact, any x is a minimizer of that particular problem. So if you think about that extreme case, what does that say? And by the way, that x will satisfy the normal equations. What I can't do is invert A transpose A. So in other words, even if A is underdetermined, like A is all zeros, or like A is a wide matrix, whatever, it's still perfectly sensible to say I want to minimize this norm. What I can do is write this expression, but what I have is that it is necessary but not sufficient for determining x, right? In other words, like any x that minimizes this expression satisfies the normal equations, but the normal equations does not uniquely determine x. That was like a lot of math words. Did that parse for everybody? And so in particular, there's one case that we've kind of left out so far in this class, which is like, well, what happens if the normal equations admit more than one solution? So think about like A equals 0 as a dumb case, right? Or in general, like if A is a wide matrix, then you expect this to happen. Then like there are certainly least squares solutions. It could still be the case that rows of A are incompatible with one another, but this equation isn't enough to determine x. So from that perspective, we can do a super weird thing. This is really weird to think about. So we have three cases. A is overdetermined, completely determined, i.e. invertible, or underdetermined. We've done cases 1 and 2, but we have not done case 3. Cool? Cool. So here is a totally bizarre optimization problem that I claim covers all three cases. I think I also wrote this in a Slack or Piazza or whatever response to a question from On a couple weeks ago, which is as follows. I can look at vectors x and I can solve the following optimization problem. This feels super weird. Here's what it's saying. This is like a totally secondary thing, right? It's saying among all of the x's that solve the least squares problem, I want to find the one whose norm is the smallest. By the way, if you're like a fancy person in like modern research literature, you would call this like a bi-level optimization problem or nested, right? Because you're saying among all the solutions to this optimization problem, choose the one that's the smallest norm. Cool? There's all kinds of really neat math if you're into these kinds of problems. Okay. So let's think about our three cases. Let's say A is an invertible matrix. Then notice we'll have AX equals B because now we can just multiply both sides of the constraint by A transpose inverse. If A is overdetermined, then the constraint determines X and the optimization objective doesn't matter. But if A is underdetermined, namely this thing doesn't determine X, now it turns out there is a unique X that minimizes the norm. We'll see that as we do our math here. Is this cool or what? So if we can solve this problem, we can solve all of the possible linear cases in one shot. How do you think we're going to do this? The SVD, because we only have one tool. Okay. So let's factor A equals U sigma V transpose like that, as one does. So in particular, if we have A transpose A X equals A transpose B, well, let's do it piece by piece. So what is A transpose A? Well, it's going to be V sigma transpose U transpose times U sigma V transpose. Yeah. So in particular, we will get V sigma transpose sigma V transpose. For now, let's use the version where V and U are square and sigma is not square. So we kind of know that this is a diagonal matrix of squared singular values, but we have to be careful. This is not sigma squared because it's a non-square matrix. Okay. Right. And okay, so in other words, and what is A transpose B? Well, okay, so it's V sigma transpose U transpose B, like that. Okay, so if we take our constraint A transpose AX equals A transpose B, notice that both of them have a V in front of them, and V is an invertible orthogonal matrix, so we could just get rid of it. So what we're going to get is the following. Sigma transpose sigma Y is equal to sigma transpose D, where we just make a few definitions. So y is equal to v transpose x, and d is equal to u transpose b. Everybody agree with me here? Like essentially, I just called this thing d, and I called well, v transpose times x y. Right? Notice that if I know y, I know x, right? Because I can just multiply it by v. Cool? So now we can make all these substitutions back into our optimization problem. And what are we going to get? Well, we'll get the following, where we're trying to minimize the norm of y subject to a much easier constraint, which is sigma transpose sigma y is equal to sigma transpose d. Cool? So I basically just did a change of variables to get rid of u and v. That's what's happening here. Okay. Notice, by the way, this is a very similar strategy to like your homework problem or Krusty's problem. Like essentially what we did is we did a bunch of changes of variables to eliminate stuff until we're just working with diagonal matrices. And this is pretty nice. Now notice there's a temptation here, which is to multiply both sides of this expression by sigma transpose inverse, but we can't do that, right? Because sigma transpose might not be invertible. It could include some zeros down the diagonal. However, it is a very simple thing, okay? So in particular, what is this constraint saying? Like if I look kind of row by row, right? Like essentially what this constraint is saying is that sigma I squared times yi is equal to sigma I times di. You see that? Because sigma is a diagonal matrix? Okay. So in particular, there's actually two cases. Suppose that sigma is non-zero, right? Well, in that case, I can divide both sides by sigma, and I'm left with y equals di over sigma. Suppose sigma is equal to 0. Does the constraint on yi do anything? At that point, the constraint is just 0 equals 0. Well, notice we wanted to minimize the norm of y, so what should we choose yi to be if sigma I is 0? 0. I like that gesture. That's good. Yeah. So in particular, what we showed is yi is equal to di over sigma I if sigma I is not equal to 0 and 0 otherwise. Notice we have completely determined y. So essentially what we've done kind of secretly is shown that this optimization problem has a unique solution, which is good. Like there's no more, like it's not like turtles all the way down where you have to like do this thing again with solutions to that or something like that. Okay. So let's kind of unravel. So essentially we have done a change of variables to y, and now we have written a formula for y. And remember that y and the actual unknown to our problem x are equal to one another up to rotation, by definition. So in particular, what have we shown? We have shown a fun formula, which is the following, that essentially x, which is equal to v times y, is equal to v times sigma plus, I'm going to define that thing in a second, times u transpose b. Remember, this thing is d. Ugh, I wish they didn't use u and v in SVD. U transpose v. Right? This is just unraveling our substitution, where sigma plus I is equal to 1 over sigma I if sigma I is equal to, not equal to 0, and 0 otherwise. Okay? So in some sense, notice, by the way, if we compare this to what's on the slide here, it's basically the same formula in the case where sigma is invertible. All we did is we said, well, if sigma is not invertible, then essentially anytime there's a 0, we just leave it alone. But we justified that that was the right thing to do. Does that make sense? So this matrix has a name. It's called A plus. The plus is kind of like, you know, like if you wrote A inverse and you got it a little wrong, then you get a plus. Which I think is the way to think about it. Like it's like trying to be an inverse, but sometimes it can't, you know? And so this object is called the pseudo-inverse. And it's one of these things that I think commonly gets used in linear algebra proofs, because just like the SVD, it exists for any matrix. You can always write the pseudo-inverse. Is it the case that A plus times A is equal to identity? Absolutely not. In fact, this is true if and only if A is, well, I should be careful. It's certainly true if A is invertible. Otherwise, you've got to be awfully careful. And it depends like sort of what direction you do your product. And so generically, actually that's not even true. Sorry, I take it back. If A is not invertible, that product's just not the identity. Yeah. And so essentially the pseudo-inverse is a mathematical convenience. Now, the second question you should ask is, should I be computing this object numerically? And I think the answer is generically probably not. Like it's often an okay thing to approximate because you're truncating eigenvalues anyway. But let's think about like what this thing looks like in the spectral universe. So let's say that I have sigma I, and now we've got like the corresponding element of the pseudo-inverse, right? So it looks kind of like 1 over sigma I, and then like a little dot there. So is this a very stable object to compute? Absolutely not, right? Like I can take any matrix, like wiggle it a little bit, and then suddenly there's a jump in the value of this the pseudo-inverse. And moreover, notice that like if I wiggle it a little bit, it's probably actually quite a big jump. Yeah? Think about it in one dimension. Like what is the pseudo-inverse of a 1-by-1 matrix? Like T. Well, it's 1 over T, except when T is equal to 0, in which case it's 0. Right? So from that perspective, this is a very unstable object to compute, because like the pseudo-inverse of 0 is 0, the pseudo-inverse of epsilon is like ginormous. Yeah? And so I think you actually see that in a lot of code for computing these objects. Like you can do it, it's a numerical convenience, like you can solve linear systems with this object, but it's awfully dangerous to use because it's very unstable. Okay? And so this is one of these objects you should only use if you have like, you can convince yourself the calculation you're going to do downstream is stable. But it is worth being aware of because it's a very common object. Sorry, I went through a bunch of slides. Any questions about that story so far? The good news is we've like glued together all of linear algebra. At this point, this is everything we could possibly do. Overdetermined, underdetermined, completely determined. Yes? That's absolutely right. So in this derivation, we're using the square u and v and the non-square sigma. And so if you think about it through, like all the operations we did are okay, because u and v are orthonormal matrices, so it's okay to invert. And then we were quite careful to define the sigma, which might not be square. It's just 0 anywhere that's not the diagonal through this little formula here. So I'll let you double check that when you're home. Okay. So essentially the kind of fun property, like pseudo-inverse, or sometimes people call this the Moore-Penrose pseudo-inverse. Penrose must have been a very prolific guy. I feel like his name pops up in a lot of weird corners of math. Essentially, it's kind of nice because it covers every possible case of inverting a matrix, or like trying to invert a matrix and failing. Okay. Now let's talk about a few other applications of SVD. There are so many. Oh my goodness. We'll talk about a few that are useful in practice. My goal was to get to the Procrustes problem by the end of lecture, which is on your homework. Sadly, I don't think we will, which means if you've managed to not do that part of your homework yet, you should read the book chapter. But we'll see how far we get. Okay, so right. Here's a nice thing that we can do. So remember that we just spent the last couple lectures talking about how it's usually a lot easier to compute just a few eigenvectors than the full set of eigenstuff for your matrix. Oops, I dropped my pen. So one question you might ask, I mean, we can certainly do that for the SVD, right? It'll be easy enough for us to compute the dominant singular values of a matrix. A question you might ask is, why is that useful or interesting? So here's a kind of fun thing that I can do, which I just erased. Okay, great. So let's say that I have the following. Let's say that I write A is equal to U sigma V transpose. We're going to write that formula a lot today. And now I think of breaking up the columns of U like that. We've got a bunch of diagonal sigmas. And then we've got like V1 transpose, V2 transpose, and so on, like that. Okay? The one thing that you can convince yourself by doing out this product is that this is equal to the sum over I of sigma I ui vi transpose. This is, by the way, just generically true for matrix multiplication, that you can kind of write it in terms of products of all the rows and columns. Notice what I've done, which is kind of fun, is like I've written A as a finite sum of rank 1 matrices, right? That's what each of these guys is. And moreover, these two things are unit length, so they're kind of nice. And sigma i's, we typically by convention sort, right? So like sigma 1 is bigger or equal to sigma 2. Oops, that was a 1. And so on. So let's think about the action of our matrix from perspective of SVD. Notice that like if I multiply A times X, so I stick an X every which way. First of all, if I have the SVD, notice that I could have parenthesized my expression like that. And what is it kind of doing? It's saying that like I take the dot product of X and VI, and then I use that scalar to scale UI, and I take a weighted sum. So in some sense, the most important terms in this sum are the ones where the sigma i's are big, right? So in particular, one thing that we can do is just truncate that sum. UI, VI, transpose X. And now I have a fast approximate way to do matrix multiplication, right? Notice that this is order n time to do that dot product, and then another order n time to scale U, right? So this is kind of like k times n squared. Let's put it all together, okay? Now, this feels a little bit goofy. I mean, it took a lot of work to compute the SVD, but there's actually one case where it's quite useful, which is as follows. I can do exactly the same thing for the inverse, assuming such a thing exists. And essentially, what I can end up with, 1 to k of 1 over sigma I, ui, pi, transpose x. Yep. Now, in this particular case, probably what I want to do is truncate so that I keep around the small sigmas, right? Because those are the biggest weight in this sum, right? So let's say that I have to solve ax equals b a bunch of times, and I'm okay with an approximate solution. Then one thing that I can do is compute just a few of the singular values that are close to 0, and then write this expression this way, maybe parenthesize that way for efficiency. And essentially what I get is a very fast matrix inverse approximation, which can be useful. So for example, we talked about other algorithms in this class that require multiplying by matrix inverse as sort of an inner loop, and we'll have many of those coming up later in this course. Now, this feels like an okay approximation. One question is, how good is this approximation? Like, there's a universe where like suddenly this matrix here is like a really, really bad version of A. We haven't actually bound it. Notice that if I truncate this sum with k terms, this is a rank k matrix. It's kind of clear because notice that the output is in the span of the first k UIs. Oh, by the way, I guess I should, if I'm being careful, it's less than or equal to k. Okay, so one question is like, essentially, what have I shown? I've shown that I can approximate A as the sum I equals 1 to k sigma I ui vi transpose. And a reasonable question you might ask is this a good approximation? Right? And intuitively it feels like yes, because like essentially the sigmas are like scaling stuff, and essentially just sliced out terms with a small scale. Right? So I think a fun thing that we'll try to prove today. Oh, oops, yeah. By the way, this object UV transpose called outer product. It's a rank 1 matrix. Okay. Sorry, I'm like not looking at my slides. I get so excited about SVD that I just start talking. But the good news is, unlike the last lecture, I can pretty much predict what's going to happen in this one. Okay. So here's what we're going to do if we manage today, is to prove a crowning result of linear algebra. How many of us have seen this before? It's called the Eckert-Young theorem. Cool. Yeah, I think it's often to see in statistics. But we're going to do a fully linear algebra version of this theorem, which says the following. Essentially, I could look at any approximation of a matrix in the set of rank k matrices. And I could, like, for all I know, out there's like some better approximation than the one I wrote on the board. What Eckert-Young says is that that's not the case. That actually, this formula that I just wrote is not only like kind of reasonable heuristically, but actually I cannot do better. Meaning that if I look at any rank k approximation, essentially the norm of the difference is upper bounded by the norm of the difference between A and the thing that we wrote on the screen. By the way, kind of a magical thing about Eckert-Young is that it doesn't really depend what norm you use, which is kind of neat. So it turns out that like this theorem is true in both the Frobenius and the 2 norm, and I believe in any norm that's sort of isometric or isotropic with respect to rotations of the rows and columns. In today's lecture, we're going to prove the 2 norm, like the spectral version of the theorem. The Frobenius norm version of the theorem just requires an extra inequality that's kind of annoying to derive. Okay? Everybody understand the statement of Eckert-Young theorem? Basically, again, it's like I can take my matrix, I can write it as a thing of most rank k, meaning that it's like outputting stuff in a subspace, and that I cannot do better than doing the SVD. Notice that this, by the way, justifies principal component analysis. Okay. What do you think? Should we prove it? I think we can prove it. Yeah, this isn't so bad. We got time. I think the textbook doesn't bother proving it, but I was reading research papers that have nice proofs, and I found a really clean one, so we're going to do it today. Okay. The Eckert-Young theorem is good for you. It like shows up all over the place. This is one of these facts that like shows up in what Hilbert spaces. It shows up here. It shows up in all kinds of corners of math, and it's just useful algorithmically because it kind of suggests that the dumb thing that we suggested on the board is the right choice. Okay. So what we're going to do today in class is prove the spectral 2-norm version of this. In fact, I think just generically for all these kinds of theorems involving approximating matrices, the spectral norm tends to be the easier case to prove. And this is because like really the spectral norm knows about the action of your matrix, whereas the Frobenius norm is like this weird thing involving the entries of your matrix, which is like not super geometric. Okay, so we're going to start by taking our matrix. Guess what we're going to do to it? We're going to compute its SVD. So in particular, we're going to write U sigma V transpose, where, and we are going to sort from biggest to smallest. Maybe I call the last guy sigma L because I'm too lazy to figure out whether it's rows or columns. It's not going to matter. Okay. So our goal here is to show that some truncated version of this thing is the best possible rank k approximation of our matrix. Notice one thing we can do is just, for one thing, just make a quick definition. We're going to call AK exactly the approximation that we like. So this is the sum I equals 1 to k of sigma I ui vi transpose, like that, where k is typically less than or equal to L. When k is equal to L, AL equals A. Right, so cool? Okay. So our proof basically takes place in 2 steps. The first thing we're going to do is just measure the approximation error of AK. And then we're going to show that if I put in any other rank k matrix, it does worse. Does that make sense? Yes? This thing? A sub L. Yeah. Basically, if I include all the singular values, then A sub L is equal to A, just by SVD. Cool. Okay. So let's bound the following quantity, A minus AK. And again, we're going to do our proof in the spectral 2 norm. The Frobenius norm proof starts out basically the same way. Okay. Well, the good news, this part of our proof is pretty easy because we have an expression for A in terms of the same pieces we use to make AK. So in particular, this is the sum A equals 1 to L. Oh, oops, sorry. That's not how you write math. 1 to L of sigma I ui vi transpose, and we're going to subtract off sum I equals 1 to k sigma I ui vi transpose, like that. So far I've just plugged in my formula. By the way, we can assume k is less than L, right? Because when they're equal, there's nothing to prove. Okay. Right, so if you think about it, these two sums have a bunch of terms in common. It's just that the L1 keeps going after the K1 stops. So in particular, this expression is the same as the sum I equals K plus 1 to L, sigma I ui vi transpose, like that. Cool? All right. Can anybody guess, like, what is the spectral norm of this thing? Let's think about it. Well, think about it this way. I mean, like, what is this matrix doing? It takes any unit vector, right? It dot products it with vi, scales ui. So far it's like kind of taken a dot product, like it's rotated that vector for sure, and then scaled it by sigma I, where sigma I goes from k plus 1 to L. Remember, they're in order, right? So the biggest one is sigma k plus 1. Yes, help me out. Please. That's exactly right. It is the largest remaining singular value. It is sigma k plus 1, like that. Let's think about why. So in particular, let's say that we plug in the, we'll do one direction of this proof, which is to show that it is at least that. Right, so remember the spectral norm is like the soup over all unit vectors that are multiplied by this thing. So in particular, notice that if I took x to be equal to v k plus 1, right, then if I call this matrix M, what is mx is equal to sigma k plus 1 v, uk plus 1. So in particular, the norm of mx is just sigma k plus 1, like that, right? So we've shown that the spectral norm is at least this large. I'll let you guys think about how to show that it can't get any bigger. It's really just basically the same, right? Like there's a dot product here which is going to be less than or equal to 1, and that's going to basically get you there. Okay. Okay. So what have we done? The good news is that like the error in the spectral norm of AK is very simple. It's just sigma k plus 1. Yeah? And that's kind of expected, right? I mean, we took this norm, we truncated it, and basically all we were left with was this guy, which is a weighted sum of a bunch of unit vectors, and that pretty much gets us there. Cool so far? By the way, this is the part of the Frobenius norm derivation that's a little bit annoying because like this little step in logic we did involved matrix vector multiply, and Frobenius norm doesn't have that property. Okay. So now we have to show that if we have any other rank K matrix, the error of that rank K matrix is greater than or equal to sigma k plus 1. Cool? This proof is really slick, by the way. Like there's some of these proofs that I think you guys could pretty much pull out of a hat. Well, all of you could because you're brilliant MIT graduate students. But some of them you could pull out of a hat immediately, and some of them you probably ask ChatGPT and then tell me that you didn't. And this, I think, falls into that latter category. So, sorry, not that I would ever accuse you guys of doing such a thing. All right, so now let's take just a generic rank K factorization. So suppose we write A is equal to x, y transpose, where x is in R m by k, and y is in R n by k. Notice that this is just a generic way to write x in A in rank k. Let me try that again. This is just, if A is rank k, I can write it in this form. Okay, so what are we going to show? We're going to show that the norm of, oh, I'm sorry. That shouldn't be A because A is our actual matrix. Let's just give it a name, B. Right, so B is our approximation of A. My apologies. And essentially what we're going to show is the norm of A minus B is upper bounded, or lower bounded rather by this value here. I'm having trouble with words today. I apologize. Okay, so, right, so what we're going to do is we're going to like make a few definitions, and we're going to make a really sneaky choice of matrix vector product that just makes this proof work out in one line. This is really clever. Yes?
Sorry. Where do you get E equals X, Y transpose from?
So remember, our goal is to show that any rank K approximation of A has worse error than the one that we just wrote. This is notation for rank K, right? Because essentially any rank K matrix can be written, if you want to use machine learning terminology, in a K-dimensional latent space, and then back out. Yeah. Okay, so, right. Here's a thing we can do. We're going to look at the columns of V. Remember that V comes from our SVD. And we're going to define a weird object, which is V k plus 1, where essentially what we're going to do is take just the first k plus 1 columns of V, like that. Okay? So what is Y transpose V k plus 1? Well, we don't know a whole lot, but what is the size of that thing? So remember that Y is n by k. So this is going to be k by, that's supposed to be next, by k plus 1. Okay, so this is a wide matrix. Now, what do we know about wide matrices? Well, all the way back in like lecture 3 of this course, we kind of justified that a wide matrix always has an interesting null space. Okay, so in particular, what we can conclude, because Y has more columns than rows, is that essentially there exists z not equal to 0 with the property that y transpose v k plus 1 z is equal to 0. Okay, so let's think about this expression for a second and make sure that we all agree with it. So essentially, this matrix has more columns than it has rows, right? It's like a chunky matrix, right? Which means necessarily its columns are linearly dependent. And so the z is like the weights of the linear dependence. Cool? Okay. So this is going to be the object that we're going to use to show that our spectral norm is no good, which is cool. This is a clever choice. I don't know, like Eckert and Young were smart guys. Okay, so in particular, by the way, notice we could scale z. So let's choose z to have norm 1 just for convenience. Okay, so here's what we're going to do. We're just going to directly upper bound or lower bound our difference. So let's look at the norm of a minus b. 2. For convenience, we're going to square it like that. Okay, so it's important not to think. We're gonna plug in our formulas for a and b, and then see that something cool happens. Okay. So first of all, what is the definition of the 2 norm? Let's do a little review for midterm. Yeah.
It's like for a matrix M, it's the largest norm of Mx over all units.
That's right. It's the biggest possible norm. So in particular, I can say this is max over all q with length 1 of the vector norm a minus b times q. For convenience, we're going to square. Cool? This is definition. All right. So this is the max over all possible q. So if I plug in any particular q, I get a number that is at most this big. Does that make sense? So what I'm going to do is I'm going to plug in my sneaky choice here. And this is by taking q is equal to v k plus 1 times z. Now notice that z is unit length, so q is also unit length because v has orthogonal columns. Okay, so I plug in this weird choice of q. If you're wondering, like, how did you get this? My answer is, I don't know, from a book. No, but like it does. I think this is sort of a clever proof. So in particular, this is greater than or equal to a minus b times v k plus 1 times z, where z is chosen above. Cool? All right. Now, why would I possibly make that choice? So let's plug in our expressions for a and b, and we're going to see that a magical thing happens. Okay? So in particular, what is a? Well, a is u sigma v transpose, by definition. Yeah? B is xy transpose, also by definition. We have a v, k plus 1, and a z. Cool? All right. So now it's all coming together. So in particular, notice if we go back to our definition, what do we have? We have that z has the property that y transpose vk plus 1 times z is equal to 0. Yeah? And conveniently, we have a y transpose, a vk plus 1, and a z. Right? So in other words, the second term of our sum is just equal to 0. Sneaky, huh? Yes, on. Ah, yeah, so why is the norm of Q1? The norms of the columns of V are all 1, and in fact are orthonormal to one another. Right? So essentially all I did, Q is equal to some vector in the V basis whose weights are in Z, and V is an orthonormal basis, so necessarily its norms are the same. This is a fancy way of saying the following: Vk plus 1 transpose Vk plus 1 is equal to the identity, right? Because it's a submatrix of V. I'll let you think about it at home. But essentially, this just comes from, like, all I did is I took all of V and I extracted some of its columns. So the columns are orthonormal to one another. And that's basically all you need, right? So this is basically just in the V basis, these are the weights, the V's are orthonormal, so that's good enough. Okay. So I'm going to hide it. See, now we can't remember. Okay, so here's our expression. The good news is the second term is equal to 0. The bad news is I just closed all of my notes. Okay, so what are we going to end up with? We have U sigma V transpose. The second term is 0, so we can just ignore it, times V k plus 1 times Z. And actually, on thinking about this expression will maybe help you convince yourself that the previous thing was unit length. That's supposed to be at times. Okay, so basically all I did was just slice out the second term. Cool? What is this product? I love the hand gestures. It's actually quite, you're very expressive in exactly the right way. It's great. But if you think about it, so what did I do? I took all of the columns of V and I transposed them. That's the V transpose. And then I have V1 up to Vk plus 1, like that, right? So this is the dot product between every single one of the V's and then some of the V's. So in particular, do you see that this is basically just like some submatrix of the identity? So, okay, what does this thing look like? So basically, well, it's just got like some, and then possibly like a bunch of like maybe zeros like that, something like that. Or the zeros are underneath. In fact, wait, let me think about it for a second. Ah, sorry. The zero, so this is tall and this is not, and this guy's short, so it should be like that. My apologies. Have I lost you guys? The second I make a mistake, you guys tune it out. It kills me. Stay with me. Your professor is a human and he makes mistakes. You know, your other, like your math professors also do. It's just that they're more confident about it. So you don't notice it until later. Okay, so hopefully we agree that this product here, it's like taking the full identity matrix and then like slicing off a few of its columns, right? So in particular, what does that mean? Well, it means that we end up with the following property, that this is equal to the sum I equals 1 to k plus 1, right? Because those are the number of columns that we have left over here, of zi squared sigma I squared. We look confused because we are. So essentially, what is going on here? Well, we've got a bunch of vector weights here. This thing is just selecting out the first k plus 1 of the z's, right? Then I scale them by the sigmas. Multiplying by u doesn't affect the norm of a vector because it's a square orthogonal matrix, so I can just ignore that, like that. And so this is what I'm left with. Okay. Now here's the thing. What is the sum of zi squared? Well, remember that I chose z to be equal to 1, or to have norm 1, right? So in particular, this number is 1. Yeah? I've chosen to kind of write it in fancy sum notation, but the z is a unit norm vector. So what's going on here? This is a weighted average of the first k plus 1 elements of sigma. Or sorry, yeah, that's right. Okay, yes?
Does u disappear here, or does it just remain as a unit vector? Like there are new set. You're summing over new sets that are basically set times u.
One more time, sorry.
Does the u actually disappear here, or does it just make a new set that is also unit?
Oh, yeah. No, absolutely. When I pre-multiply this thing by u, I get a different vector, but its length is the same. Yeah, good question. But basically, like if I multiply a vector by an orthonormal matrix, its norm doesn't change. That's all. Sorry. Thank you. Okay.
It was just a set that it was still set in the sum.
All good. Okay, so we have this expression here. It's a weighted average of the first k plus 1 sigma I squareds. What's the way to make that weighted average as big as possible? Well, I should put as much weight as I can on the biggest element of that set. Similarly, what if I want to make it as small as possible? I should put as much weight as I can on the smallest element of that set. Now remember, which direction are we trying to bound this norm? We want to show that this error is high, right? So the kind of direction we want is like that, right? So in particular, essentially what we've argued is that this is greater than or equal to sigma k plus 1 squared. Right? It's a weighted average of sigma 1 through sigma k plus 1 squared. The weights are positive and sum up to 1. So if I take all those weights and stick it on the very last guy, that's going to make it as small as I can. Notice that I just proved the theorem. Because if we go back, we started by the norm of a generic difference between A and any rank K matrix, and we squared, but whatever. we show that it is greater or equal to the k plus first sigma value, singular value squared. So in essence, take the square root of both sides, which we can do because these are all positive numbers. What did we show? Well, this thing is exactly the norm of the difference that we started with the matrix we defined. And so we're done. Isn't that cool? So Eckert-Young theorem, ta-da! So this like stuff that you're doing in statistics class where you take the rank K approximation by doing SVD is actually justified. It's not just like a fun heuristic that like somebody told you to do in stats class. This really is the right thing to do for principal component analysis. And moreover, the reason you compute it with the SVD is exactly this fact here. Cool? Any questions? Yeah, Hamid. That's exactly right. So if you want to prove the Frobenius norm version of this theorem, you're going to end up like cycling a bunch of traces around, which is indeed a trick we're going to use more and more as we move forward in this class. Like spiritually, the proof is basically the same. It follows the same two steps. But actually proving the first equality there is slightly more annoying. Yeah. Yes?
You said that this holds for all matrix norms, or I might have misheard you?
Well, it holds for these two. And generically, I believe it is the case that under some pretty reasonable assumptions on your norm, like that it's rotation independent and that orthogonal matrices have norm 1, you can get pretty close to proving this fact. Like this is using some very simple linear algebra. Yeah. Any other questions? Okay. So I'm looking at the clock, and there's basically no way that we can prove the last thing we're going to do. So I will give you a quick summary, and then we'll start with it next time. Here's just a fun thing. Like basically anything that you care about in basic linear algebra, you can probably write in terms of the SVD of a matrix. So here's a grab bag of a few others that we're not going to prove in class. If you're looking for good ways to practice for your exam, it would be to show any of these identities. All of which, the proofs are all basically the same, which is you drop in A equals U sigma V transpose, and you just like grind forward. Yeah. But essentially, anytime you want to do some, by the way, the condition numbers with respect to the spectral norm. Anytime you want to do a calculation with a matrix, the first thing you should do is drop in the SVD, which is not to say that's the algorithm that you should use at the end of the day, but it is to say it gives you a baseline. And so that's where I would start. What we'll do in our next lecture is talk about something which I know is also in your homework, so I hope you did a little bit of reading ahead, which is we'll talk about the rigid alignment problem. This is sort of a special case where one step of a really famous algorithm called iterative closest point in geometry, where essentially you're given two 3D scans of an object, and maybe you mark a few points in common between the two, and your job is to find a rigid motion. This doesn't work when you have a left and a right hand, that align them onto each other. And so essentially we need to find a rotation matrix that rotates one shape onto the other and a translation vector that drops one on top. Okay, so in our next class, we will cover how to do this in closed form using SVD. You can also peek ahead in the book because a simpler version of this expression is used on your homework, and the book walks through the proof in a pretty straightforward way. Yes? Do you get cheat sheets for the exam? That's your question? We just did all this beautiful stuff with the SVD, and all you want to know is the exam. Oh, you kids kill me. Yes, we will send all the information you need about that soon. Yeah. All right, so with that, I will see you guys on Wednesday, and have a delightful rest of your Monday. Let's see, did I manage to actually record today?